Hello students, hope you are all doing well. Welcome to another video by Quick Study. Today we will start another topic of IGCSE Physics, and our topic for today will be solids, liquids and gases. So let's look at the properties of solids, liquids and gases. So solids have particles which are closely packed in a fixed orderly structure, whereas their properties are fixed shape and volume, high density, incompressible, strong intermolecular forces. Let's look at the particle arrangement of liquids. The particles of liquids are closed but can move past one another. The properties are fixed volume, no fixed shape, take shape of the container, and they have medium density, and they are also incompressible. They have weaker intermolecular forces than solids. But gases are on another level. The particles of gases are far apart and move freely. The properties of gases are they have no fixed shape or volume, they fill up the container. They have low density and they are compressible. They have very weak intermolecular forces compared to solids and liquids. So when we are talking about gases, we have to talk about Boyle's law. So basically, Boyle's law states that the pressure of a given mass of gas is inversely proportional to its volume when the temperature is held constant. So obviously, it has a formula which is P1 V1 is equal to P2 V2, where P1 and P2 are the initial and final pressures, whereas V1 and V2 are the initial and final volumes. So they are basically equal. So let's look at the explanation and an example to understand what Boyle's law really is. So if the volume of a gas decreases, which means compresses, the gas particles have less space to move around, leading to more frequent collisions with the walls of the container, which increases the pressure. Conversely, if the volume expands, the particles are more spread out, collides less frequently, and the pressure decreases. For example, compressing air in an air syringe decreases the volume and increases the pressure. So let's look at an example which we can do with this formula. Atmospheric pressure is about 100 kilopascals, which means basically 100,000 pascals. Some air in a sealed container has a volume of 2 meter cube at atmospheric pressure. What would be the pressure of the air if you reduced its volume to 0.2 meter cube? First, we write down what we know. Here, P1 is 100 kilopascals, V1 is 2 meter cube, and V2 is 0.2 meter cube. So we have to find out the second pressure, basically, the final pressure. So we know the formula is P1 V1 is equal to P2 V2. So if we do the triangle method, it would be P2 multiplied by 0.2 uh, is equal to 100 kilopascals multiplied by 2 meter cube. So the final pressure would be equal to 100 kilopascals multiplied by 2 meter cube divided by 0.2. The answer would come out as 1000 kilopascals. There's another formula which basically connects pressure and temperature. This law states that the pressure of a given mass of a gas is directly proportional to its temperature in Kelvin, considering that the volume is kept constant. So obviously we have a formula for this, which is P1 divided by T1 is equal to P2 divided by T2. Here P is the pressure and T is the temperature. This is the initial pressure and temperature, and after that, that is the final pressure and temperature. So the explanation of this is basically if the temperature increases, the pressure also increases and vice versa, assuming that the volume is kept constant. So let's look at an example for this. So let's take an empty tin and put out the lid on tightly. You heat it using a Bunsen burner until the temperature of the air inside is 50 degrees Celsius. What is the pressure of the air inside the tin? The temperature of the room is 20 degrees Celsius. So we already got two temperatures. First, we have to write down what we know. P1 is 100 kilopascals. Considering that this is the atmospheric pressure, we have to remember this, that atmospheric pressure is 100 kilopascals. So we have P1, T1 and T2. So the starting temperature is 20 degrees Celsius, but we must change this to Kelvin. So we will learn more about how to change temperatures from Kelvin to Celsius shortly. But the basic idea is we have to add 273. So 20 degrees Celsius plus 273 would be 293 Kelvin. The end temperature, or T2, would be 50 degrees Celsius and must also be converted. So it would be 50 plus 273, which would be equal to 323 Kelvin. So as the formula goes, P1 divided by T1 is equal to P2 divided by T2. So P2 would be equal to, doing the triangle method, P1 multiplied by the final temperature divided by the initial temperature. So the answer would come out as 100 kilopascals multiplied by 323 Kelvin divided by 293. So the answer would be 110 kilopascals. While dealing with different temperatures of different masses, we must know about one thing, which is the specific heat capacity. It is basically the amount of heat energy required to raise the temperature of 1 kg of a substance by 1 degree Celsius or 1 Kelvin. The formula for this is Q is equal to mc, temperature change, and multiplied by the energy. So basically it is Q is the heat energy, m is the mass, C is the specific heat capacity, which is denoted by joules per kg degree Celsius, and the temperature change is denoted by Celsius or Kelvin. So let's take an example for this. For example, water has a high specific heat capacity, which is about 4,184 joules per kg degree Celsius. And iron has a lower specific heat capacity, which is basically 450 joules per kg degree Celsius. So let's do an example which we can do with this formula. If you fill a kettle with 300 grams of water at an initial temperature of 15 degrees Celsius, how much energy is needed to make the water heat up to boiling? The specific heat capacity of water is 4,200 joules kg degree Celsius. So we have to write down what we know at first. So here the mass is 0.3 kg, as we are converting it from gram to kgs. The specific heat capacity is 4,200, and as the boiling point of water is 100 degrees Celsius, we must do the temperature difference. The initial temperature given here is 15 degrees Celsius, and the boiling point is 100 degrees Celsius. So the temperature difference would be 85 as we subtract 100 by 15. So we have to write down the equation, which is Q is equal to mc multiplied by the temperature difference. So we have to substitute the correct values into the equation. Remember that the energy, which is the heat, which is the Q, is also a difference of two things. As we are doing for the temperature, the same can be done for the heat. So we have to substitute the correct values, which are, for energy it is 0.3 kgs multiplied by the specific heat capacity, which is 4,200 joules per kg degree Celsius multiplied by 85 degrees Celsius. So the energy would come out as 107,100 joules. So the answer would come out as 107100 joules. As we said before, now we will be talking about temperature scales and the conversions in between them. So we all know about Celsius, which is water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. But for Kelvin, it starts at absolute zero. Absolute zero is the temperature where there is no motion or heat found. 0 Kelvin is equal to minus 273.15 degrees Celsius. We already used it in the previous example. Water freezes at 273.15 Kelvin and boils at 373.15 Kelvin. And there's another one called Fahrenheit, which is water freezes at 32 Fahrenheit and boils at 212 Fahrenheit. So these are the basic conversions in between them. Let's look at some examples we can do to understand better how to convert temperatures between different temperature scales. So the first one is, at what temperature does water freeze in Kelvin? Water freezes at 0 degrees Celsius. To convert 0 degrees Celsius to Kelvin, we have to do 0 degrees Celsius plus 273. So the answer would be 273 Kelvin. So what is the room temperature in Kelvin? Typical room temperature is taken as 20 degrees Celsius here. So T would be equal to 20 degrees Celsius plus 273 Kelvin. The third question is, what temperature is 400 Kelvin on the Celsius scale? So in the Celsius scale, the temperature would be 400 Kelvin minus 273 degrees Celsius, which would be equal to 127 degrees Celsius. So we have to basically plus or minus 273 to convert between Kelvin and Celsius. So in this video, what we have learned is about solids, liquids, and gases. We have learned about Boyle's law and the law between pressure and temperature. We learned about specific heat capacity and also learned about how to convert between different temperature scales. So now we can basically convert to any temperature from Celsius to Kelvin or even to Kelvin to Fahrenheit. That's all for today, students. Stay with us to learn more about physics and other courses as we post regularly on our channel. To learn more about our online tutoring service, do visit www.quickstudy.uk.